about unimodal representation, specifically visual representation. That's what we will be discussing. We will go over a relatively large amount of information today because I really want to get you, although CNN, you could debate, now we have visual transformers. CNNs are still widely used, and so we want them, and there's a really high chance you end up having to use them as part of your project, and also they come with good intuition behind them. So I will remind a small reminder about heterogeneity, and then we'll go in image representation. So I just want to remind us, like, when you look at a modality, remember, like, modalities, why multimodal? Multimodal is the science or study, let's call it the study of heterogeneous and interconnected data. And so each modality, and that was also a question on Tuesday, like, what is a modality? I on purpose in this class going to be extremely generous and call almost everything a modality, just because I don't want to start like saying is like, is a written language and spoken language, are they one or two modalities? They are definitely homogeneous, like there's a lot of similarity, but as I highlighted, like for example, the structure a little bit different, the way also you segment data in spoken language. So you have to realize that it's not just black or white. There's really a spectrum from heterogeneous to homogeneous. And we highlighted at least 6 dimensions. This is not like exhaustive. In fact, if you have feedback, we'd love to get that feedback. That very separate from this is that the survey paper we shared with you will share an optional form for feedback. Like, this is like, doesn't give you, it can be even anonymous, any kind of feedback about this, but this is a separate topic. But yeah, heterogeneity at the first level is like, when you look at a modality, try to think, if I analyze that modality, is there like a unit of analysis? Is there like some basic building block that will be used for this analysis? So in language, it's kind of easy because we have words that are kind of obvious. And I used the term granularity on Tuesday, and it was a little bit confusing. So that, what I mean by that is that there's a decision that I need to make as a scientist, or like, what is going to be my granularity? I could use words, I could use noun phrases, I could use characters, because maybe I'm interested to study like new words that are created in some languages. Or I can use a speaking turn as well. In the case of visual, I could use like pixels or edges or object or group of objects. So that's like these representation. And as we start in speech, it's not always clear where's the start and the end of a unit of analysis. Is it a phoneme? Is it a what's called an acoustic frame, like, or speech frame, like that, like time slice window of like 20 milliseconds, which is kind of arbitrary, but that could be also a unit of analysis. And what is the distribution, like, without like looking specifically at like the ordering, but more like the distribution of my data? Is it a balanced data set? Do I have more of something, more, less of do I have a high frequency? And the structure, which is quite related. In fact, these two, I will say, is very close to each other. And there, it's a lot more about the structure of the data. The structure of the data. And here is it could be structure that is seen, that is explicit, like sequence of words, or it could be something that is explicit or implicit or latent, like really the grammar. In fact, if I take a picture of you guys right now, there is also an aspect. I will take a photo, it's 2D, but there's also this hidden information about 3D information that's also there, that's like hidden in it. And so there's a lot of information that, and yes, I can kind of approximate from 2D, but it's not explicit there. I need to do some processing to get it. The information, and that's something we will discuss more in a week about when we revisit this topic. But if I take an element and I say how much real information there is in it. So if I say there is I take language and then I analyze it by character, by character, by character, by character. But then it's good. It's very precise, like it's very fine-grained. But each element, how much information do I really get within an element is going to be much smaller. If I decide to take my granularity at the speaking term level, then each element, because they're like englobes a lot of information in it. And between modalities, you're going to see a lot of difference there. Like if you look at speech and you decide acoustic frames, yes, there is information in an acoustic frame, but it's much smaller than what you will get in a sentence or even a word. This is why often we suggest in your course project to have, yes. For the tactile modality, yeah, that's a really good one. So you said, what about the tactile, you asked? The single element, yeah. So that's really interesting. So the lowest one will be definitely like each individual sensors. I mean, usually for tactile, there's like really fine-grained tactile like sensors on it. At least some gloves, for example, would have. But often you have this kind of fuzzy region that kind of are not, and that's the problem with like sometimes you have clear like this is one unit of analysis, this is another. Tactile is another, like you kind of have like maybe each finger, if it's a glove, like each finger could be like a unit of analysis, but is this sensor or this one really going to be like, it's a lot more fuzzy. And that's a good example. Speech has the same issue. You often have like, it's not there's often bleed over between phonemes. And so that's going to be a challenge for that. But yeah, for tactile, these, what you define as a unit analysis, but you should always at least make an effort to kind of think what it should be, even if it's a little bit fuzzy, because it may guide your way you represent this. Yeah, good question. Yeah. And then the noise, like very different from different modality. I love language also. It has some noise, but it's a relatively clean representation. But yeah, images, gloves, EEG, electrical, these sensors for the brain, like these have a lot of noise. In fact, sometimes you need to have multiple trials to kind of remove that. So you want to take that missing data. And finally, which was also some questions like his heterogeneity or granularity, all this, like shouldn't be like task relevant. And yes, many times the task will in fact require you to revisit all of these because it end up like being on one specific aspect that you will study. But I on purpose study them like kind of task independent at first, to kind of think that because there are things that are task independent, but then now I have a specific task and maybe I don't care about like gender information. In fact, maybe I don't want this. Maybe it becomes a bias that I don't like. I want to be careful about, or that there's another aspect of the data. So yes, definitely the relevance to the task is important. So we call it dimension of heterogeneity. We've been debating that because we study this because we are working about multimodal. We could have also called kind of modality profile. If we look at it in a really unimodal way, each modality has its own kind of profile. But for the purpose of multimodal, we will be particularly interested in the differences of those profiles. So it's a little bit like semantic at that point, but at the end of the day, you want to study each modality, but also with the purpose of multimodal, we want to study the differences and be aware of those differences. So they're kind of building on each other. You need to do profile. So today, for example, we'll study the visual image modality and try through different description to try to understand a little bit the elements the distribution, the structure. These last one we'll study in later part of and task with a little bit later. But yeah, how do you represent an image? And I told you that the most basic one is like just pixels, and that's also with the question earlier about like how is it for the tactile? Like it could be just at really low level. Really, what is, I will say, a kind of established representation in the last, I will say, about 10 to maybe 12, 15 years, but 10 years definitely, is that now images became an object representation. It's almost a list of objects. So each object will often have maybe a label associated. What's nice now is that these, and that there's some work in early 2000 that did that, but more recently we're revisiting it, where objects are not just objects, but they also have like attributes associated with it. And some of it will be hopefully human interpretable, or maybe some attributes will be kind of, you just do a clustering of all the objects that you have. Because if you have a lot of human like knowledge top down, you can always go and get and use that. But if you don't, then you can go bottom up and kind of cluster your data and try to do your best, giving them like label 1, label 2, attribute 1, attribute 2, just trying to do your best in clustering it. What you will see is that you will see these representations come not just like discrete one, but also will have feature vector, feature deep representation with it. So you will sometimes have them like age, but like maybe appearance of the object. How do I summarize the appearance of the object? I could just try to describe what they're wearing, or I could do a deep neural network and a dense representation of that appearance. I just want to share that this, where we are now, comes from a little bit of a long line. It's only one slide, but it comes from a nice long line of research. In fact, a lot of the early stage, like 30 something years ago, images were represented as edges. And how do you compute an edge on an image, on a grayscale image? How do you compute? Yes? Yeah, exactly. In fact, it's a discrete gradient. It's a gradient. It's a spatial gradient. If you do an X gradient, like look at changes, and so you can in fact, I will show you visually what it looks like, but you can pass a kernel to it and it nicely give you the edges. And if you want the edge horizontal, then you do one type of kernel, which will be dark and white, and you just run that. That's a discrete gradient. And if you do it the other way or in any directions, was there a question? Yeah. Yeah, so you can run, and there's ways to get like all the gradients at once, a kind of like a circle, and you run it over. You're kind of getting any edges, but usually what you will do is different type of edges with different kernels. So edge detection has been a big thing, I don't know, in the 90s. Histogram of gradient. Even one of our own software, OpenFace, is using underneath that histogram of gradient, and they're still there. And what it says is that it said like, okay, let's use 8 different gradient direction and just do a histogram of how much activation each of these. And you have to think back then, we had kind of accepted that objects are kind of a bag of local features. It was kind of accepted. In fact, it took some time. Back in the days, if you wanted to detect an object, it was template based. You take an object like a dog image and you run it over your image and find dog. But around that time, it was kind of getting accepted that object will be kind of a bag of local features. And if I describe locally really well the object, like a mouth corner, like a face. If you find a bunch of mouth corner, eye corners like if you find enough of these evidences, you probably got a face. Where they happen, you really be, unless it's a painting, a weird painting, like you will, it's a face. So a few details. And so then the question is, a lot of work was like, how do I describe locally really well? And histogram of gradient was like, if I want to describe this point really well, let me compute 8 different gradients or 16 different gradients and just get the amount of activation for each of those directions. And that will be a good way to describe how much edges in each direction there is. And the idea is like, this is not really useful, that point, because there's no edges, there's no change of color. Any kind of change of color are the useful one. And so optical flow, at that point, there was an acronym SIFT, S-I-F-T, which was a little bit a histogram gradient for that. I will also bring, because this is early 2000, in fact, one of the first almost commercial phase detector, when you were having a good old-fashioned camera in it, then the cameras had a phase detector in it in early 2000, and that was with those Haar detector in this. So there, what do you get from this one? Which kind of edges you will get? Horizontal edges. Horizontal edges. You get the vertical edges. So these you get horizontal and vertical, and then you get a different gradient. These are a little bit more interesting. So they look at a different pattern of white, black, white. So it turned out like one really useful one was this one. In fact, the inverse of that for the eyes: dark, white, dark. Like this is really good to detect faces. Really good one. And it turned out that our brain is also using that, or the eye specifically. There are Gabor filters in your eye in early stages of vision. Sorry, you may or may not see well on the display, but they are mostly a little bit more fine-grained version of those Haar wavelets, and they're different orientation. So we know that humans are doing that. Like they take the image and they're creating kind of responses to different kind of these filters. So that's what. So then build from that. If you take an image and you want to really understand it, then you could run those like 3 filters. So these 2 are like vertical edges and horizontal edges. And there I showed you like just looking for any edges. That's the one that kind of look for any kind of edges. And on purpose, I'm going to suddenly start using a name here that you're going to start recognizing. I'm going to call them convolutional kernel. So why are they convolutional? The convolutional, it's not to make it fancy and anything. It's just convolutional because convolution is well established, especially in speech processing. It's a process where you take a template, really what it is, it's a template, and you just run it through your data. Usually it's on a 1D, so you run it on a 1D signal, and you just multiply. It could have been called the multiply kernel, but it's convolution. There's a slight thing, and it's inspired from speech. But it's inverse. There's a small inverse. There's a small kind of a transpose happening. So it's not exactly just multiplying that kernel with each input, but you could. It's much easier to just remember it as a multiplication, and you just run it through all. So really, what they did here is take this and just run it, usually on a grayscale version of the image, and just run it through all, and that's what you get here. So convolution just means, if it confuses you, just think multiplication of a small template. A kernel is also just a fancy word for a template. So multiplication template, convolutional kernel. Now you have a nice one. So now building from that, and I'm going to give more details in a second, is that convolution kernel from the 90s, but came back in early in 2010, even more popular, is taking this idea of convolution, pushing it even further. I just want to mention, and don't worry, we will talk about the visual transformers as well. And I should mention that objects and taking an image and summarizing as a list of objects is kind of a, oh yeah, and 40. Yeah, is a little bit of a simplification. So although we do a lot of work on objects and probably 95% of your projects are going to be a list of objects, you should remember that images have a lot more to it. One well studied is image segmentation, segmenting all the object in it. But even that is not complete. Like there's something really interesting happening here. So the extended arm, so the part, it's not just the object, but a part of the object. There's a lot of very interesting work and extension of what we will use in most of our research. There are also dedicated, often those detectors, like object detector, they want to remove all the variants related to facial expression because their goal is to detect is it a face or not. So every variation of facial expression will not be very well encoded in those representations, CNN representation, if they were trained for face recognition, face detection, and then they will just, their goal is to ignore all the variations. So there's some software, in fact, I told you histogram of gradient. One really nice one, OpenPose, it's a little bit older now, that came around the same time, a little bit after Kinect, Microsoft Kinect, but yeah, just from 2D images. These are by now, I would say a little bit older. If you really want the state of the art, there are newer ones. Often you get a little bit better, not super much better, but, and we tried, it's kind of hard to keep track of all of those toolbox, but we tried to put some of them as a starting point, and then you can build from that. A little bit outdated, but we're doing our best to keep it updated. So CNN, I want to spend a little bit of time on that just because we will use it as a building block. And the intuition behind convolution neural network, there are many of them, but one of the main intuition is that it's trying to reflect on how the brain is, at least it was motivated that way, is that the brain has, at the lowest level, has all these edge detectors, and we know that, like, if I remember all my cognitive science literature, like V1 and all of these different modules that have been studied, in part of the brain have been studied. There's some, not all, but there's some evidence that at least some these get aggregated even in the brain. And there is, for some object, in fact, there's faces specifically, there seems to be in the brain dedicated neurons for certain objects. And so the idea is that there is a hierarchy in the brain. Maybe we could go and there's a hierarchy also in neural network. There's really interesting work, which is trying to correlate brain, someone watching an object and looking at their brain imaging, and then looking at a CNN, and there is some correlation between the two. Take it with a big grain of salt, this kind of research, but it's interesting that there is some correlation with how the human is also doing. So the key advantage here, it is inspired somewhat of the visual cortex. There is this level of abstraction, and there, as we will discuss, is there's translation and variance. We'll discuss in more detail that. And those templates that are going to be learned, and there's fewer parameters than just multi-layer perceptor. I will go in all of these key advantages in more detail. But translation and variance, I think by now I hammered it enough. So if you were to train with a multi-layer perceptron, what it means is take an image that's a bunch of 0 and 1 and just put it in a vector, simple vector, and put it in a multi-layer perceptron with only one output, which is it the face up or down? you can probably learn that well. But then suddenly the image is there, and then that will not work on that multi-layer perceptron unless you do that recentering beforehand. So that's a little bit what the translation. But it was a good question on Tuesday on the follow-up on the notes. It's like I kind of emphasize that there's translation invariance, but as you will see also in the CNN, it's we also want to take into consideration. I mean, for some time, having a person next to another is a really good piece of information, and you want to keep that information. So I say translation invariance. I should have put it a little bit with a like, it's kind of again maybe more of a spectrum. It's like if I move slightly, I should not like suddenly get completely off. That's what I mean by translation invariance. But having an object on the left of another object or on the right of another object, that may mean a lot for a specific task. So translation invariance is something, it's not like you want to ignore it completely, because in that case, the CNN will not be designed like it is. The CNN will be designed, if you want to ignore it completely, you would run your templates on the image, and the response will be a bag of responses, like a bag of feature, like a bag, completely ignoring any kind of local information and spatial information. I'm going to share a little bit more details, but in this case, with the CNN is designed to keep a little bit of that local information. And so it's not, I just wanted to make clear, local invariance or translation invariance is something you would like to handle, especially local variation, but you want to keep some information. So, but conventional MLP, definitely, because they really just take this image, and for them, each pixel, they don't really know that this one was next to the other. They just see it as an input independent entry. So CNN are kernel based, so it helps a lot with the translation invariance and will reduce the MLP. So I want to emphasize, so I told you that human, and this was really well studied. So human have that kind of Gabor filter. So you can predefine them. In fact, there's probably no reason in most CNN to probably learn the first layer. The first layer is quite well studied of a CNN. In fact, what really happens is the CNNs end up learning something that look a lot like Gabor filters. And then we're like, oh, good, that's what we expected. But what's hard is that we don't know what the next step should be. But the low level are a lot like Gabor filter. That's a lot what we will see in this. So the CNN will learn by itself. So this is a predefined set. But one of the main interesting thing is I'm not going to predefine the kernel. In fact, the main weight matrix of my neural network, the W, what will be encoded in it are those kernels. That's in fact, what is a CNN? The W is just a bunch of kernels. And that's really the only thing that's in the CNN are a bunch of kernels, a bunch of what it is, multiplicative templates, convolutional kernel. That's the main thing it is. So there's many interesting papers that went ahead and started looking at what was learned in those different layers of those neural network convolution. I want to remind us, so if I learn this very fine-grained kernel template, and then I run it through it, then I get a response map. So my question to you, how do I train, let's say really simple, how do I train a neural network that will always, when you give it any image, give you an output that is exactly equivalent to that convolution kernel? Let's say that I don't want you yet to learn that kernel yet. Let's say I give it to you, but eventually you will learn it. But I want you to just learn a neural network. I want you to design a neural network that will always, for any image, give me a response map that is, I think this is kind of this part here. This is kind of this part. I think it is MIT, but I'm not sure. So how do we do this? So one way to learn this mapping, you can learn this mapping if you have enough image training data set like that had like where you did run this on the input image and get this, and you get a lot of this. You can probably train a multi-layer perceptron to do that, which will go for all pixels here and again there. But that will be a lot of connection, a lot of weights. You're not taking advantage. So the convolution layer does two assumptions. It does the first assumption. It says to decide what the value of this output pixel should be, I don't really need the whole image. I only need a local. Like this output here is really just based on this. Like these pixels have nothing to tell me about this output here. So this is this first assumption will be that will be shown is instead of connecting everything here, instead of having all of them, I'm going to say, hey, I only need a small window to decide what this should be. So instead of having all pixels connected to all output, you're going to connect only a subset, which is kind of equivalent to running locally, let's say a 3x3, and giving me an output. The second assumption is the way I decided this pixel or this output based on this input is also the same way, the same weight. I will decide, like, sorry, I'm moving. I will decide this pixel based on it. So, like, I don't need to learn a different kernel for the beginning and for the end. Like, it's the same kernel everywhere. So I will do what's called tying the weights. Really, like here in this version, every edge, every arrow will have a different weight, which will mostly mean that the way I detected the output here will be different than how this, but here I'm making a big assumption and that I have only one kernel, and that's the same kernel that can be run through it. So how do I go very efficient from there to there? Just one matrix like this. It's one matrix. In this case, it's a kernel of 1x3. It could be a different one. And so it's a kernel of 1x3. And so if I multiply that matrix, and then I will get that output. Now, in reality, what's really nice is it can be done really efficiently. So I got one response, we'll call it a response map from this. And then often this W is going to be not 2D, but 3D. So you have multiple of those kernels, multiple of those templates. Okay, so maybe some for edges this way, some edges this way, some all of those edges. And because the W are, in fact, parameters that are going to be learned, so really the kernel is something that will be learned. So really what it does is going to do its best to learn parameters in such a way that it can output the response map. Now, the training of a CNN, the real loss is not going to be the response map, but we're going to take the response map and going to summarize it and going to try to detect output like object classes. What is the object in it? So the response map will become kind of a latent representation. It's still going to be part of the intermediate representation, but the real loss, the real like supervision, the gradient coming out will come originally from, did I correctly predict the object in the image or not? And it will propagate, but at some point it will propagate into this. and then we'll continue, and that's eventually how the weights will be coming and will be set for it. So this takes a little bit. I mean, for some of you who've done computer vision, this is easy. This you've done it for some of you, but this is, you will do it at a first level. That's how you do, and you're going to combine these over time. But how do you combine? So we talk about two things that were important. We like for the convolution layer, but then there's another part which is, how do I combine? How do I summarize information over layers? And back in the days, we were just calling it averaging or something, but now we call it a nice term, pooling. So we're pooling. Again, sometimes we like to create terms, but like pooling, it just means most of the pooling is often just a max or average pooling. Really what it means is that I have the response map, which at the beginning, if I get an image of 640 by 480, and I run it through my first layer of convolution, what is the size of my response map? 640 by 480 is the same size. So what they will do after that is just say they do pooling. So they will go and one layer there of it, and they just average, usually either max or average pooling. And there's a lot of papers have been written on trying to compare average versus mean or max or other version. At the end of the day, they have a small, there's a small difference in them, but yeah. So at the end of the day, you take your 640 by 480, and then you do one of these, and you get a 320 by 240. Now, reality is what these models have been trained is usually 64 by 64, the image. So if you give it a 640 by 480, the first step it does is squish it into 64 by 64, and then continue after that. There's a lot of interesting work that has been done on trying to not squish, so I'm not gonna, but often what they will do is just force everything in 640 by 64 by 64, and then after that, the next layer after the pooling is 32 by 32, and then you go 16 by 16, and the 16 by 16 or 8 by 8 start being really interesting. So in fact, one of the first CNN was a bunch of convolution, maybe convolution, which is kind of a W. I told you like it's the W multiplication, but because it's a neuron has a nonlinear activation function. So some of the early packages that did CNNs, they will separate the linear aspect of a neural network from the activation function. So that's why you see the ReLU as a separate one. It's just the activation function there, and you may not see there's a pooling that reduces that. What's really nice is then at the end, at that layer here, so 64 by 64, you get an 8 by 8. So I told you, CNN doesn't get rid of all the translation and variance, because at the end here, up to here, you still have an 8 by 8 matrix, and that each of them 8 by 8 tells you within it what were the templates that were there, what was the information. But it did at that stage of the CNN, you have not thrown away the translation information. What they finally do is just put this 8 by 8 into a one-layer neural network, feed-forward neural network usually. At that point, you lost all your local spatial information. But up to that point here, you still have, if you had a 64, so this influence from these pixels will only affect, in this 8 by 8, will only affect that output here. Okay, so that is there are many extensions of this. I would just mention one of them that was interesting was residual network, which at that point, what it is is that when you do these, what it turned out, there was a dream of like, oh, can we go beyond like 4 or 5 layers? The problem is the gradient. That was something that had been studied. Why, in fact, when we look at recurrent neural network, yeah, I will show you. In fact, that's a great question. There's a paper that which is about visualizing CNN that will do something similar. So it really depends how you engineer the next steps after that 8x8. If you go and you take that 8x8 and you run it into a neural network that outputs, like say 1,000 neurons, and then run that 1,000 through, that gives you, let's say 300 something 20. By the 320, you could, by looking at weights, but it's not like, it's kind of a fuzzy a little bit, because that neuron, but first you have 320, they each of those 320 ended up taking that 8x8 and found different ways of fusing that 8x8 to get you there. So the link between that and that 8x8 is still there, and you can back propagate the gradient and kind of learn that, and that's somewhat the but it often, you get often at least 1 or 2 or 3 layers after, and by the time you're really making that prediction, you've done a lot of nonlinearity, and you've merged your data in ways that is not the most straightforward. It's not impossible, but it's not the most straightforward. But I'm going to share a paper which said, hey, why don't, instead of going and making it non-interpretable at that last step, what if I made it really directly from that 8x8 to my class label, directly to my class label, and that way I will know which part of the image was useful for each my class label. I may not get as good performance because that more fancy one will probably have done turn, but at least I will be able to visualize it. Yeah, good question. So the residual network, we'll talk more on Tuesday, but the main aspect was that we would, if your gradient is, you have many layers, there's something about a vanishing gradient. So like if you realize that you got it wrong, okay, you got it wrong. So you have your gradient back propagate, but every layer you're kind of losing a little bit of the power of that supervision. And so these residual are really interesting, which is, it says, don't try to take the input and really create something new, but work on something that I can add to X. Like, is there something that I'm missing in my X that you could give me to it? So these are going to learn, it's not going to be a template and the response to that template, but more it's going to try to learn something in the image that could be added to the image itself. So it's a slightly different way to look at it. I just wanted to bring that. It's like, how do you visualize a CNN? Oh yeah, sorry. Yeah, this is sorry. This, you could call it a skip connection, residual connection. I don't know if I have time to go in the, but you could almost see it as a skip connection. They're different implementation where this is definitely a skip connection, but it's a skip connection that is designed in such a way that the inside the skip is at the end of the day, because I'm doing a summation here, I'm in fact learning something that is going to be added, and because it's something that's added, it's kind of a residual, but this could be seen as a skip connection. Yeah, there's a lot of great work, especially these days, because people want to get like things on the cell phone, and so there's a lot of great work of training these models with a lot of parameters and trying to reducing them, either teacher, student, but there's a different paradigm to like take this almost as a teacher, and you're trying to teach that like simpler model to give, and there's different ways you could say give the same output or give the same intermediate. There's a lot of interesting strategies there, doing it efficiently. Yeah. So visualizing, and maybe I will stay, this will be the last section I will for today, is like, how do you visualize? And so you could take these last, like those, at that point, think is still 8 by 8, but here suddenly you are fully connected. And so you could still take these embeddings and just do PCA. PSNE is just a fancy version of PCA, principal component analysis. Like you just take the two main principal components, eigenvectors, and just display your data. But as was mentioned, I want to bring it, this was ask a question, is that instead of having those multiple layers and losing interpretability, what if I go from that convolution and say it's a slightly different from what I suggested, is like, say I have a response map for each kernel. I told you, like I have like usually 64 kernel. And what I can do is say which of those kernel here was the most helpful for detecting my each class label. So I kind of have a one-to-one kind of mapping between each of those and the class label. So that is CAM, class action activation map. So these are the activation map, and I'm going to learn a linear mapping. The grand one goes a step further and say I have all of these, and I'm going to do a one layer, but I'm also going to use the gradient to see how it reproject into the image. And I'm not going to go in as much detail because it's also going to be part of your reading assignments. So you can go in more detail, but just wanted to give you some there. I will go quickly. This is not as important. It's just that how do you get, oh, sorry, yeah. That would be another approach. Here, the goal was that you still want to aggregate the different response. You're hypothesizing that each of those activation maps are not, it's not just that one of them is useful, but that all of them may be useful. And you're trying to see what is the relative usefulness from each of them. But if you knew that only one of them is really useful, if I understood the suggestion, you could just get an MLP and see which of them is the most predictive, if I understood. Okay. Oh, so that is kind of an end. I don't know if it is. We can discuss maybe offline after, but this is a little bit of an ensemble idea and there. So for the purpose of this, we will be, for the highlight form, the third segment being the matching. If you can discuss a little bit, but we're not gonna, we're gonna give everybody the third segment for free for the highlight form because it was only a few minutes on this. My phone didn't vibrate, but yeah. Okay, so now what we will do is for the next 20 minutes, we will have, where's Alex and Gabrielle? Okay. So, so at this stage, before you stand up, because once people stand up, then it's a lot harder. This is a team matching. We will be here if you have questions at some point. But the goal is to meet with other students. Hopefully, you looked at the list yourself. We have different corners. Did we decide the corners? Yes. Okay. You want to mention, Alex? I think the A, B, C, D, E, F. Okay, you swap. Yeah. Let's be consistent. Okay. Yeah. A, B, C, D, E, F. Okay.
And then G can kind of help a little bit. So if you want to have a name tag, there are a couple extras, just come down and see.
Okay. And we will do on purpose 10 minutes. And then after 10 minutes, we'll kind of say, hey, if you have a second topic you were thinking, why don't you go and also chat for that? If you want to stay in that, you're like, this is my topic. This is the only one I go. But yeah, so A, B, C, D, E, F, and G. Okay. Okay. Thank you.